Unlock the potential of artificial intelligence. Welcome to deep learning and generative AI.
Large language models operate by predicting the next most likely token in a sequence. While the underlying math is straightforward, scaling that process has enabled the creation of autonomous enterprise infrastructures. To understand how text prediction scales into autonomous systems, we must establish exactly where these models sit within the broader computational landscape. This diagram maps the current taxonomy of AI. The outermost ring represents foundation models. These are advanced machine learning architectures, such as transformers, pre-trained on massive multimodal datasets to encode statistical relationships. Within that sits generative AI. This is a specialized subset of foundation models trained explicitly to generate novel content, including images, text, and video, based on learned patterns. At the center are large language models, or LLMs. These deep neural networks learn the statistical structure of language from massive text corpora. They predict tokens in a sequence to execute text generation, translation, and reasoning. LLMs function as statistical engines, executing pattern recognition at a scale that simulates cognitive reasoning. Before developers could achieve this scale, natural language processing faced a severe structural computing limitation. On the left, a recurrent neural network reads tokens sequentially, creating a bottleneck where the model forgets early information. Bypassing this, the transformer architecture on the right uses self-attention to process all tokens simultaneously, capturing long-range dependencies instantly. The process starts with subword tokenization, fracturing text into discrete indices. These enter the self-attention engine, where an embedding matrix generates 3 projections: query, key, and value. Using a softmax equation, every token dynamically calculates its relevance to all others, weighting context with mathematical precision. This diagram compares to 2 primary transformer setups. On the left, encoder-only models process entire sequences simultaneously to build dense, bidirectional context mappings. This makes them effective for tasks like sentiment analysis or named entity recognition. On the right are decoder-only models. These utilize masked self-attention to predict the next word based exclusively on preceding context. This architecture is the standard for high-quality, autoregressive text generation. Self-attention effectively shifted language processing from a memory-constrained sequential timeline into an accessible geometric map. Calculating these dense attention matrices across billions of parameters requires an immense scale of data and hardware infrastructure. The training pipeline has 3 stages. Stage 1 is pre-training, where the model consumes petabytes of data via next token prediction. Stage 2 is instruction tuning, teaching the model dialogue through supervised fine-tuning. Finally, Stage 3 is preference alignment, using a reward model to ensure truthful, harmless outputs. Strict scaling laws govern these results. The power law graph shows error rates decreasing linearly as model size increases. This optimal frontier requires roughly 20 tokens per parameter. Crossing these massive parameter thresholds unlocks emergent capabilities, like spatial reasoning, appearing suddenly without explicit training, as shown on the staircase. Intelligence in these systems is an emergent physical property of massive, optimized data compression. Once a model is trained and its neural weights are frozen, developers interact with it through in-context learning. This table illustrates prompting as gradient-free programming. At the top is zero-shot inference, where models predict outputs based purely on their raw training. Below, one-shot and few-shot inference provide completed examples within the prompt, setting a pattern that guides complex logic without updating internal weights. However, scaling dense transformers quadratically is becoming economically and physically unsustainable for the industry. To address this, new architectures are evolving. On the left, Mixture of Experts routes tokens to specialized subnetworks, keeping computational costs low. In the center, state space models achieve linear time processing, improving memory efficiency. On the right, compact small language models run on edge devices, removing cloud dependency. The future of LLMs lies in engineering these specialized, efficient architectures, rather than merely increasing the size of dense networks. When deploying these models, organizations must choose between proprietary and open-weight ecosystems. As this table shows, proprietary models offer robust managed infrastructure, while open-weight models provide total deployment control and custom fine-tuning capabilities. Currently, enterprise adoption favors proprietary APIs. This bar chart illustrates that most organizations are prioritizing the immediate availability of managed services from providers like OpenAI and Google over local deployment. Deployment strategy is moving away from simple text generation and toward the use of models as autonomous agents. This diagram outlines how LLMs act as autonomous reasoning engines. In this workflow, the central agent block receives an input and uses its reasoning capabilities to orchestrate tasks across external tools. Following the downward arrows, the agent autonomously executes a database lookup. It retrieves specific internal order context and cycles that data back into its own reasoning loop to refine its next move. Simultaneously, the agent routes gathered information to the external tools cluster shown on the right. It can trigger calculations or access vector databases to synthesize a final, grounded output. Enterprise value derives from an LLM's capacity to act as a cognitive routing engine for external infrastructure. Deploying these engines at scale introduces hardware and memory challenges that are distinct from those found in the training phase. The left panel illustrates the physical reality of LLM ops. Hosting billions of parameters requires distributed GPU and TPU orchestration, which is vulnerable to silent failures like hallucinations that demand continuous benchmark monitoring. The center panel shows the training scale bottleneck. Moving petabytes of data across networks introduces critical physical memory dependencies and massive management challenges. A critical production bottleneck is the key value, or KV cache. During autoregressive generation, this cache grows linearly with sequence length. As the graph shows, this creates massive memory pressure in real-time environments. To manage this, developers must use advanced throughput systems like page detention to prevent complete memory exhaustion during inference. Systemic risks also exist at the software level. The top left quadrant highlights prompt drift, where updates to closed-source base models can unexpectedly break established prompt pipelines and orchestration frameworks. Furthermore, the bottom left quadrant addresses the challenge of integrations. Engineers must build strict compatibility layers to bind non-deterministic generative text into rigid, deterministic external APIs. Managing large language models at scale requires solving the physical constraints of distributed memory and the non-deterministic nature of generative logic.